India occupies a massive footprint on the globe, spanning from 8 degrees 4 minutes north to 37 degrees 6 minutes north. From west to east, it stretches over nearly 30 degrees of longitude, encompassing a total landmass of 3.28 million square kilometers. That 3.28 million square kilometers represents a mere 2.4% of the Earth's total land area. Despite this constrained footprint, it houses roughly 17.5% of the entire global human population. Bisecting this dense concentration of humanity is the Tropic of Cancer, cutting straight through the middle of the country at 23.5 degrees north. This single latitudinal line splits the subcontinent into two distinct baseline climate zones, a tropical environment in the south and a subtropical zone to the north. The extreme diversity across the subcontinent follows a predictable mathematical logic, a geographic matrix where topography and climate define the limits of the biosphere. Mastering Indian geography requires looking past isolated trivia. It requires understanding an interconnected chain of cause and effect, tracing how bedrock and mountain ranges directly dictate the shape of the biosphere. The foundation of this matrix lies in the south. The Peninsular Plateau is one of the oldest, most geologically stable landmasses on Earth, originally a fragment of the ancient Gondwana supercontinent. Over millions of years, tectonic forces gave this rigid block a slight but permanent tilt toward the east. That subtle gradient serves as the gravitational blueprint that dictates the flow of nearly all major southern river systems today. While the south is ancient and stable, the north consists of young, tectonically active fold mountains formed by continental collision. At the northernmost edge lie the Trans-Himalayas. This range includes the Karakoram, which holds K2, the world's second highest peak, a summit often mistakenly assumed to be part of the Greater Himalayas. Moving south, we hit the actual Greater Himalayas, or Himadri. Built around a massive, continuous core of solid granite, this unbroken wall of rock supports the highest elevations on the planet. Below the Himadri sit the Lesser Himalayas, and finally the Shivaliks. As the youngest and outermost range, the Shivaliks are primarily composed of loose, unconsolidated river sediments, making the entire zone highly vulnerable to massive landslides. Because these ranges form an immense physical barrier, human movement and trade rely entirely on high-altitude mountain passes, narrow, treacherous gaps carved by nature that serve as the only viable entry points through the rock. These massive tectonic structures act as the ultimate physical containers for the subcontinent. They determine exactly where water is allowed to flow and where massive weather systems are forced to stop. Those mountain walls give rise to the Himalayan river system. Because these rivers are antecedent, meaning they existed before the mountains fully rose, and are continuously fed by massive high-altitude glaciers, they flow perennially, year-round. As the Ganga-Brahmaputra system descends into the flat plains and flows eastward, the rivers slow down. They drop massive amounts of sediment, forming wide, braided channels and massive river islands right in the middle of the flow. The Peninsula River system in the south operates under entirely different rules. Carving through ancient rock, these rivers are older and fully mature. They lack glacial sources, making them completely reliant on seasonal rainfall. Remember the eastern tilt of the Deccan Plateau? That gentle, elongated slope forces rivers like the Godavari and Krishna to travel long distances, losing speed and depositing heavy loads of silt at their mouths to construct extensive, fertile deltas. Conversely, west-flowing rivers like the Narmada and Tapi are trapped in steep, narrow rift valleys. They rush rapidly down a short, sharp gradient straight into the Arabian Sea, washing away sediment to form deep estuaries instead of deltas. If you look closely at how these water networks branch out, you can read the terrain beneath them. A dendritic pattern with tree-like branches indicates flat, uniform plains. A radial pattern, where water flows outward like spokes on a wheel, proves the existence of an elevated central dome. Whether a river flows all year, dries up in winter, builds a delta, or cuts an estuary, it has no choice in the matter. The water's behavior is entirely bound by the tectonic bedrock and the physical slopes beneath it. That bedrock dictates the path of water once it's on the ground, but getting the water there requires an atmospheric engine. The southwest monsoon is driven by a simple physical law. Land heats up and cools down much faster than water. As the intense summer sun moves north, a thermal equator known as the Intertropical Convergence Zone shifts over the Gumba Plains. This bakes the landmass, causing the air to rise and creating a massive continent-scale low-pressure vacuum. Nature abhors a vacuum. To fill this void, high-pressure, moisture-heavy air is violently sucked in from the Indian Ocean, splitting into two distinct branches as it wraps around the southern peninsula. When the Arabian Sea branch slams into the towering wall of the Western Ghats, the wet air is forced abruptly upward. It cools rapidly, condenses, and dumps massive quantities of water on the windward side of the mountains. This is orographic rainfall. By the time those winds cross the peaks and descend the eastern slopes, they have been bled dry. The air warms, its moisture capacity increases, and it leaves the leeward side of the mountains in a parched rain shadow. Further north, the monsoon winds hit Rajasthan but produce almost no rain. The Aravalli Hills run directly parallel to the wind's path. Without a perpendicular barrier to force the air upward, the moisture simply sails past, leaving behind the arid Thar Desert. The distribution of rainfall across India follows strict physical rules. The water falls exactly where the geometry of the tectonic walls intersects with the trajectory of the atmospheric moisture. When you combine the ancient bedrock with the relentless rhythm of the monsoon over millions of years, you get the final geological output, the soil profile. In the north, the Himalayan rivers constantly grind down mountain rock, carrying it into the plains. They deposit these fine sediments to form incredibly fertile alluvial soils, the newer Khader and older Bangar, which dictate the high agricultural yields and immense population density of the region. Black soil forms from basaltic lava, retaining immense moisture and splitting into deep cracks that allow air to reach the roots. In areas blasted by intense heat and heavy monsoon downpours, the soil undergoes severe leaching. The heavy rain washes away silica and nutrients, leaving behind laterite, an iron-rich soil that bakes into a hard, brick-like crust under the sun. The vegetation maps directly to this moisture gradient. Zones hit by extreme rainfall support dense tropical evergreen forests. Move inland where rainfall drops, and the canopy opens up into tropical deciduous woods that shed their leaves to conserve water. At the extreme edges, where the great rivers meet the ocean, a unique biome emerges. Mangrove forests thrive in these tidal deltas, physically adapting to the salty, oxygen-poor mud by pushing spike-like breathing roots up above the waterline. A region cannot choose its agricultural output or its biodiversity. The vegetation is locked in by the soil chemistry, the soil is locked in by the rainfall, and the rainfall is locked in by the topography. When we zoom out to view the subcontinent as a whole, it becomes clear that none of these geographic layers operate in isolation. They are running simultaneously, stacked on top of one another. We can see the proof of this system in the local ecology. The Indian rhinoceros is biologically tethered to the dense, marshy grasslands of the Northeast. That habitat exists only because the massive Brahmaputra river system constantly deposits wet, fertile alluvium across the flat valley floor. In stark contrast, the Asiatic lion is confined exclusively to the Gir region in the west. This environment is defined by dry, deciduous scrubland, the direct result of specific regional soils combined with the severe moisture deficit of the monsoon's rain shadow. If glacial melt accelerates or monsoon winds shift, the planting season and river discharge lose equilibrium, threatening water security for millions. Mastering the mechanics of this matrix transforms geography from a memorized map into a predictive tool for the